second.
Okay.
Everyone can.
So, um, so this is my research, and the title is basically, as you can see, predicting the detectability of gravitational waves from PSR J0737-3039, which is a binary pulsar system, which is really rare in the universe. And so how scientists or physicists plan to detect that is through the use of the Laser Interferometer Space Antenna, or LISA. And in this case, I use a quadrupole approximation approach. Next slide, please. Yeah, so first of all, what exactly are gravitational waves, right? So gravitational waves turn out to be ripples in spacetime created by the movement of massive objects. For example, the sun, the Earth, actually everything creates gravitational waves. It's just that lightweight objects in the universe don't, it's just not that significant. And reminder that although people might think that the solar system is just like static relative to the entire universe, but that's actually not the case. Galaxies are constantly moving, revolving around a black hole in the center, and they're also moving on their own because the universe is expanding. So, gravitational waves were first observed by LIGO in 2015. As you can see on the left, I have the image of setup of LIGO, where they have this laser source going in, which is basically laser source is basically so. What's significant about this is that LIGO is actually very, very, very like it's a very large scale project, as you can see. It pretty much goes from like Washington to I think that's Texas, and it takes like 10 milliseconds for light to travel that distance. Um, and so even that distance is not enough to detect like low frequency waves. So that's why we have LISA now, which is a space project, which is a basically a detector that's being set up in space and has a much larger radius. Yeah. Okay, next slide. So why this specific system? Why this binary pulsar system? So it turns out to be the second binary pulsar discovered, and it's relatively close to the Earth at only 1,150 parsecs. And basically, the low eccentricity and short orbital period result in greater gravitational effects. And it also has a 87-degree inclination angle, which pretty much allows it to only look at I would say one polarization. So think of it as like one direction of gravitational waves. So this actually simplifies the whole calculation process for us. So the first binary pulsar discovered is actually named the Hulse-Taylor pulsar, and what makes this system a better candidate than Hulse-Taylor is that first of all it's much closer. It has a way shorter orbital period. So you can think of it as a let's say two balls like whirling around each other, and obviously the one with that has a shorter orbital period would have a much stronger would create a much stronger wave. Yeah. So next slide. So yeah, this is the quadruple formula that I used to calculate the whole thing. You don't have to worry about understanding this, but I basically wrote a program for this in Python, and then I just inputted all the data available on the internet. So the quadruple formula is kind of the simplest method to estimate gravitational wave strength, and it is the leading term in multiple expansion. And I remember one of the questions I got most often was that why did I use this formula? Well, first of all, like I don't have the computational ability to really use the multipole expansion. Um, and this one is pretty much enough for a system like the system I'm investigating because of the fact that it's like low eccentricity and it's like close to Earth. So this is actually enough in this case. Um, And yeah, basically my third bullet point explains it. Tidal effects and spin effects are minimal because first of all, it has low eccentricity, and neutron stars don't really have spin effects. Okay, next one. Yeah, so results in discussion, pretty straightforward. The gravitational wave frequency was 0.226 millihertz, and the peak polarization for each, I guess, the peak polarization overall is that number, and the changing length of the object. Changing length basically means how much the gravitational wave changes the length of our laser. So that's within the picometer range of LISA. So it's directly detectable, but the frequency is actually too small for LISA to actually detect. Yeah. So next slide, please. So what can we do to what can we do to improve this whole system, right? So on the right you can see the setup of LISA. It's a very, as a complex system, and very long arm length. But that's still not enough. So first of all, we could increase arm length, but that's really difficult to implement because that involves probably like trillions of dollars in like the budget. So a better way is to actually use the noise to noise algorithm that I found, which actually suppresses acceleration noise, and it is a deep learning model. So you can always feed it information and I guess predict the gravitational wave strengths. And you can also use a resonance detector to amplify spatial warp. That's actually way more complicated, but I don't think I have enough time to go over it anyways. So yeah, next slide, please. Yeah, and I think that's it. Yeah, thank you.